Good afternoon, everyone. This is Sentan from Aalborg University. Firstly, I would like to say sorry for being not able to present physically due to my personal reasons. I will now introduce a resilient control framework for enhancing cybersecurity in microgrids. And this is the outline of today's presentation. I will first give the research background and objectives. And next, I will introduce how to build a DC microgrid model. Following that, I will present 3 proposed methods to deal with different types of attacks in microgrid. The conclusion is given in the end. In the past few years, there is a green transition in the use of more renewable energy sources worldwide. Denmark has now reached nearly 40% of renewable installation capacities, as you can see from those figures. But how can we integrate so many renewable sources into an energy system? The answer is the use of microgrid. Compared to AC microgrid, the DC microgrid has the advantages of having no harmonic frequency synchronization issues, so it is widely used in multiple applications, for example, the household applications and electric vehicles. With the development of communication technologies, the microgrid is nowadays turning into a cyber-physical microgrid. It consists of 2 parts, cyber system and physical system. And importantly, in the cyber system, the data are transmitted between controller and smart devices through wired and wireless networks with different communication standards and protocols. The increased digitalization of microgrids can on one hand achieve the advanced monitoring and diagnosis function. It can also help to improve the control performance, to improve the energy efficiency, for example. However, on the other hand, it will increase the vulnerability of cyber attacks because we are dealing with more communication-based devices than before. The vulnerability of microgrids come from different aspects. First, the misconfiguration and poor administration will increase the vulnerabilities. Second, the increasing use of Fairfields and massive connections of smart devices will also make the system easily to be hacked. Third, the remotely accessible tools and mobile devices can expose the system details to people, making it vulnerable. As you can see from this figure, if an attacker knows some knowledge from computer science, he or she can tamper with the communication link, thus causing physical impacts on the microgrid. This table shows the different impacts of attack on different parts of microgrid, from generation to consumption. For example, the attacker can compromise voltage regulation devices, tamper with the measurement, tamper with the device readings, or even affect the protection system. So, in order to protect power grids from cyber attacks, multiple projects have been carried out. As can be seen, the main actions here are based on risk assessment, threat analysis, data protection, attack detection, and attack mitigation. So, based on this background, the research question is how to design a secure protection method for microgrids in the case of different attack scenarios. In our case, sensor attacks, link attacks, and actuator attacks. And to answer this question, we propose 3 methods. First, we propose to use an observer-based method to detect sensor attacks, and then we propose to use consensus check-based method to detect link attacks, and finally, we would like to mitigate actuator attacks with resilient control method. Now I will talk about how to make a microgrid model. The microgrid can be considered as a connection of multiple distributed generations, where in each DG it consists of a power source, a converter, and some load. Moreover, a typical hierarchical control is implemented to control the microgrid. So we can formulate a microgrid model by considering the converter model. As can be seen, there are three critical points that could be hacked in the system, which cause sensor attacks on the measurement channel, link attacks on the communication channel, and actuator attack after the controller output. Let's go back to the microgrid model, as there are two energy storage components, inductor and capacitor, so we have two differential equations. And then we can transfer the differential equations to a state space model. Next, I will introduce the proposed method one by one. First is the use of observer to detect sensor attacks. The main idea is to design an observer that can estimate the system measurement using the system model and control output. And the estimated results are compared with real measurement in real time. If the estimated results are different with the measurements, then we refer that there is a cyber attack on the sensors, and we will discard the measurement output and use the estimated results instead. For our case, we use the unknown input observer, and the structure and equations are shown here, where the matrix F, T, K, H are unknown matrices that need to be designed. This slide gives the introduction of designing the observer. I will not present too much details because it is widely used in existing works. For our work, we use the optimization-based methods to design the observer based on the stability criterion, robustness criterion, and sensitivity criterion. To show the effectiveness of proposed observer, some experiments are carried out. In this configuration, 3 DGs are connected to formulate a microgrid. We change the load at 5 and 10 seconds and inject a cyber attack at 15 seconds. This figure shows the voltage and current dynamics, and this figure shows the residual dynamics. As can be seen, the residue increased rapidly after the injection of cyber attack. The case is nearly the same in this test. We change the voltage between 5 and 10 seconds, and at 15 seconds, the attack is injected. As you can see also that the attack can be quickly detected after 15 seconds. Next, I will introduce the consensus check method to detect link attacks. First, let's take a look what are the variables in the communication links. There are voltage and current signals from neighbors. Those variables are controlled in proportional with each other. So based on this, we can propose an evaluation method to justify the trustworthiness of data transmitted from neighbors using a proposed indicator C here. The C is a confidence value, which is expressed like this, and the first term is a filter to filter out the measurement noises. The second term consists of a consensus error and the threshold. And if there is no attacks, then the consensus error will be 1, and C will also equal to 1. If there are attacks on links, the consensus error will be greater than the threshold, making the confidence value converge to 0. To verify the effectiveness of proposed approach, 3 attacks are injected in communication links. Similarly, I change the voltage and current first, and then inject a cyber attacks here. As you can see, the confidence value can indicate the happening of cyber attacks on both channels. As you can see here and here. This is another values of attacks on communication links. This is the last case. I'll show the feasibility of proposed approach. Next, I will introduce the resilient controller to mitigate actuator attacks. The objective of this resilient controller is to guarantee the stability of the system under cyber attacks. Those are the structures of a proposed resilient controller for both grid-forming converters and grid-feeding converters. Here, we introduce a new state variables for the controller with the capability to compensate for the attack impacts and achieve the system stability. And here are some results. We change the voltage and current at T1 and T2 second, and then at T3 and T4, we inject attacks on different actuators. And as you can see, with traditional control, there is a voltage tracking errors and current tracking errors. However, with the proposed approach, there are no tracking errors. The same case results is here, where a sinusoidal attacks are injected at T3 and T4. And as you can see, there are tracking errors here and here, and the proposed control is able to achieve no tracking error performance and guarantee the system stability. So in summary, we propose an observer-based detection to detect sensor attacks. We propose a consensus check to detect link attacks. Finally, we designed a resilient control to mitigate actuator attacks. Those three methods formulate the proposed cyber-resilient framework for microgrids. And some simulations and experimental results are carried out to verify the proposed approach. Thank you all for the attention. Thank you.